Hello everyone, I'm Lokesh. Today I'll be discussing the Ozone architecture in detail and some of the performance improvements which we have done. A little background about myself. I'm a senior software engineer in Cloudera. I hold PMC and committer privileges for Apache Ozone, Apache Ratus, and Apache Hadoop. I've been contributing to these projects for the past 4+ years. Let's start with a basic introduction about Ozone. Ozone is a distributed object store. The namespace comprises of volumes, buckets, and keys. It has accessibility via the object store, file system, and S3 API. It started off as a sub-project in Hadoop, but currently it is a top-level project in Apache. Let's dive a little deeper into the architecture. So Ozone provides its own implementation of Hadoop-compatible file system API. This API is part of Apache Hadoop, and it has been developed and promoted by the Hadoop community. All the major big data applications today access storage via this API. Similarly, all the major cloud providers, storage providers, provide their own implementation of this API. So Ozone also provides its own implementation, and that is called as the Ozone file system. Big data applications can access Ozone using Ozone file system, and non-big data applications can access Ozone using the S3 API. Ozone has been designed to coexist with HDFS in a cluster. So what that means is Ozone data nodes and HDFS data nodes can share the same physical host and disk. It has been designed to not interfere with HDFS services. Let's have a deeper look into the HDFS architecture, and then we'll see what all improvements Ozone has done in its own architecture. The HDFS comprises of data nodes and a name node. The data nodes are the physical host storing the file data. These data nodes manage the disk or volume on a physical host, and they also send periodic block reports to name node. Name node would analyze these block reports and identify any under-replicated or over-replicated blocks. For under-replicated blocks, it would make sure that the block is replicated to some other data node. For over-replicated block, it would make sure that excess blocks are deleted. The name node manages the namespace. It consists of a namespace map, which is a mapping from file to list of blocks. These blocks comprise the file data. And then there is a block map, which maps a block ID to a set of data nodes storing that block. If we look at the namespace map and block map, these are of the order of number of files and number of blocks in the cluster. A typical name node would face a lot of GC pressure beyond 300 million files. So this is because the entire namespace of HDFS is kept in RAM. So now let's look at the Ozone architecture. The Ozone separates the block layer or the container layer. The name node of typical HDFS cluster has been divided into two separate components now. One is SCM. This is the cluster manager. It receives container reports from the data nodes. We'll see what containers are. So this is the manager which will make sure that the containers are sufficiently replicated. A container is a list of blocks, and this is a level of indirection. And by default, a container would be 5 GB in size. So the data nodes are similar to HDFS data nodes. They still manage the disk and the storage physical host. But instead of managing the actual blocks, it is now managing the containers. The number of entities due to this container abstraction reduces by a factor of 10 or 100x for data nodes as well as SCM. So now these data nodes are sending container reports to SCM, and SCM is making sure that all the containers are sufficiently replicated. In case of under-replicated container, it would schedule a replication. And for over-replicated containers, it will make sure that the access replicas are deleted. Similar to name node, SCM would maintain a container map. The container map would have a mapping from container ID to set of data nodes containing the container replica. So as we discussed, namespace, name node has been divided into two separate metadata components. One is the SCM, more of container manager, and then there is Ozone manager, which manages the namespace. Ozone manager keeps only a working set in RAM. So it has the mapping from file or object to set of blocks. Every block is represented by a block ID, which is a combination of container ID and local ID. Container ID identifies to a particular container, and local ID is specific to that container. So Ozone Manager keeps only a working set in RAM. This is a major advantage in achieving the scale of building keys in Ozone. Further, the abstraction of container, which reduces the number of entities that the storage layer has to deal with, that also helps in increasing the storage capacity of a typical Ozone cluster. Then Ozone also has a recon server. The recon server is an extension of FSCK. FSCK is a command line tool in HDFS to find missing blocks or corrupted files. So recon server is not a tool, it's a background service. It has its own UI, which admin or user can look at to find missing containers or to get an overview of the cluster. Ozone provides a very clean separation of block layer and namespace layer. This is a major advantage in providing more simplicity to a typical Ozone cluster. Ozone carries forward the best of HDFS. There is horizontal scalability of petabytes in I/O. So HDFS cluster scales to thousands of data nodes. Similarly, Ozone scales to thousands of data nodes. It has a fault-tolerant storage layer. Every container by default would have 3 replicas. The storage and compute can scale independently. And the Ozone carries forward the strong Hadoop security model, rolling upgrades, and it also provides ACL and range support. In terms of scale, theoretically, Ozone can reach to 1 trillion objects. Ozone cluster has been tested with 10 billion objects today. The trillion objects the scale can be achieved by some optimizations for small files and some other optimizations. Then data node density. The typical data node capacity for HDFS cluster is around 100 TB. Beyond that, there can be some pressure on name node due to dense block reports and some other issues. Ozone can support a data node density of data node capacity of around 400 TB today. This is largely due to the container abstraction. Ozone SCM has to deal with much smaller number of entities due to the container abstraction. The heap is tied to a working set, and it is not a function of number of files or blocks. So that brings a better manageability. The Ozone metadata components do not have to face the Java or GC issues which are typically seen in HDFS name node. There is faster startup, as we discussed. The data node has to give container reports, and these container reports are easier to fetch because of the relatively lower size or the number of containers in a data node are lower compared to the number of blocks. Master and data nodes can be co-located if needed. This is good for our embedded system use case. Some of the design principle which Ozone takes forward, it provides strong consistency. This is due to the Raft consensus protocol. All the metadata and data operations in Ozone happen via the Raft consensus. Ozone uses a very simple architecture. There is a clean separation of block layer and namespace layer, and a central master architecture, just like HDFS, which scales to thousands of data nodes. So this also provides operational ease for administrators or users. It uses proven building blocks, Raft, ProxDB, Hadoop security. All of these technologies have been tested and they work really well in other open source projects, and many companies have also tested these technologies. Ozone is 100% open source. It has been part of Apache Hadoop since day one, and today it is a top level project in Apache. So let's look at the write and read key workflow in Ozone. For writing a key, Ozone client would do a create key call to Ozone Manager. Ozone Manager then makes allocate block request to SCM. SCM would allocate the block. Every block is associated with a container. Every container is associated with a pipeline. So what is a pipeline? Pipeline is a set of data nodes where that container is stored. So once this block information is received by the client can communicate the data nodes, and it can write its data to these set of data nodes. So all this data write happens through Raft consensus protocol, which makes sure that the data writes are consistent. Once the client has written all of its data, it can make a commit key call to Ozone Manager, and that will update the namespace. For reading a key, client would make a get key call to Ozone Manager. Ozone Manager returns the list of key location infos. This list contains the block information. Every block has an associated pipeline, so which is the set of data nodes where the container is stored. So for reading a block, client can communicate or make a read request to the data nodes in order to fetch the block data. So this was a brief introduction of the architecture. Now we can look at the namespace and storage layer in detail. Ozone namespace comprises of volume, buckets, and keys. Volumes are like user accounts in Azure. Buckets and keys are similar to what S3 provides today. Ozone is strongly consistent system. This is due to the Raft consensus protocol being used for metadata and data updates. Ozone provides atomic directory renames today. The renames and encryption are only supported at bucket level. ACLs are supported at volume, bucket, and directory level. We do not really recommend using ACLs in nested directories because that can hinder the performance of recursive APIs. Further, Ozone also supports danger-based prefix policies. The namespace can be accessed using Hadoop compatible file system API as well as the S3 API. Ozone Manager keeps only a working set in memory. So this is a fraction of number of files and blocks in the Ozone Manager. Further, the metadata in Ozone should be stored in SSD. This would reduce the cache miss latency in case corresponding file or directory is not present in the working set. Ozone Manager stores the entire metadata in ProxDB. All the metadata updates, directory creates, file creates, every metadata operation is Ozone Manager namespace, happens through Raft consensus protocol. In future, sharding can be done at bucket or volume in Ozone Manager namespace to scale the Ozone Manager much more. Let's look at the storage layer now. As we discussed, storage layer is strictly separate from namespace layer. The data nodes and storage container manager together form the storage layer. Container is a basic component of the storage layer. It is a set of blocks, by default 5 GB in size. All the data writes inside the container happen via Raft consensus protocol. Every container has a unique container ID inside SCM. Every block inside the container has a local ID, which is specific to that container. So block is represented by a combination of container ID and local ID. Data nodes manage the physical host. They manage the volumes and the containers which are stored in that host. So a typical data node would also manage which volume the particular container should be created inside the data node. And then it sends periodic container reports to SCM. SCM is a cluster manager. It manages all the data nodes. It makes sure that all the containers are sufficiently replicated in the system. Let's look at the structure of a storage container now. So a container comprises of data files or chunk files. These files store the data. And then there is a RocksDB instance to store the metadata related to container or blocks. So for every block, there is a metadata entry in RocksDB, which tells which file that block is stored in. It also contains other metadata information like checksum and other information related to that particular block. RocksDB also stores the other metadata like deletion metadata and other metadata related to the container. So the container structure allows for some other improvements. We can use for small blocks, which are smaller than say 1 MB in size, can be stored directly inside RocksDB. So this is a great improvement for very small files in the cluster. Further, the compaction of block data can be done. So multiple blocks can be stored in a single file. So that is another optimization which can be done. And the container structure allows that optimization. A container would typically exist in open or closed state. In open state, the container can accept data writes. And in an open state, the container is associated with a data pipeline or a Ratis pipeline. So the number of open containers which Ozone maintains at all times is equal to number of disks into number of data nodes. So this makes sure that all the disks in the entire cluster for all the data nodes are equally used for when there is heavy data writes happening in the cluster. Then there is a closed state. Whenever a container reaches its configured size of 5 GB, or if it hits a failure, the container will be moved to a closed state. On failure, the container is moved to a closed state to provide consistency guarantees. Since we know that a container is replicated on 3 nodes, in order to reconcile the final state of the cluster, it is important to close the container and not allow any further data writes. Apache Ratis is a Java implementation of Raft Consensus Protocol. So Ozone uses Ratis for the data and metadata replication. In metadata replication, there is the Ozone Manager. There are multiple Ozone Manager services can be run in order to provide a highly available metadata service. So this is the typical configuration. There would be a leader OM, and then there would be 2 follower OMs. Similar configuration would also exist for SCM. There would be a leader SCM and 2 follower SCMs. All the metadata operations like create volume, create bucket, file creation, and then other important container operations in SCM would go through Raft Consensus Protocol. So that is how high availability is provided for these metadata services in Ozone. This similar configuration also exists for data writes. So by default, the container is replicated to 3 data nodes. There is a leader data node and 2 follower data nodes. The leader data nodes accepts the data write request from Ratis client or Ozone client. And these data write requests are forwarded to the followers. Once majority of these followers have committed or written the data, the successful reply is given to the client. So this is how the Raft configuration looks like. There is a leader node. The leader node accepts the client request. It will add the request to its own log, and then it will forward the request to the followers. The followers then would add the request to their own log. So once majority configuration or majority approval has been reached, that is, in a 3-node configuration, the leader node would wait for one follower to reply that the follower has applied the corresponding entry in its log. So once that validation is done, leader can give a successful reply to the client. Raft replication is usually used for small updates, metadata updates, but Ozone uses Raft consensus protocol or RATIS for data writes as well. So for data writes, there were some optimizations which were done. The data write is not done in the RATIS log or the log which we saw in the previous slide. The data writes happen directly to the disk. Only the metadata operations are stored in the log. Further, the Raft log, the RATIS log, can be stored in a separate disk so that minimum seek penalty is given to the data. So this is how a typical Ozone architecture looks like. We have multiple data nodes. That is the storage layer. We have the metadata components, Ozone manager and storage container manager. Then we have S3 gateways. These gateways listen to S3 requests and they forward those requests to Ozone manager data nodes respectively. The S3 bucket can be mounted in a kube container today, and S3 buckets can also be accessible using the S3 browser. Further, Ozone also provides accessibility using the Hadoop compatible file system, Ozone file system. So that was how architecture of Ozone looks like. We can now dive a little deeper into the some of the performance improvements. These are subset of the total performance improvements which have been made at Ozone, and these are the ones where I have been involved with. So the performance improvements can be categorized into the metadata performance improvements and data path improvements. So metadata has, it requires high throughput. So one basic improvement which was done here was to use a read-write lock. Read-write lock, as we know, multiple readers can access the Ozone Manager namespace using the read lock. And this instantly provides very high throughput for read request in our typical metadata service. And then horizontal scalability. So Ozone cluster, as we discussed, can scale to thousands of data nodes. It is important for all of these data nodes to be available and all of these data nodes to be efficiently used. So one of improvement which was done here was around block allocation. Earlier, block allocation used to happen on using a set of containers. So SCM would maintain a set of containers, and whenever a block allocation request would come, it would select one of these containers and then allocate a block inside that container. The change which was made here was to add a level of indirection. So now instead of keeping a set of containers, it was keeping a set of pipelines. Whenever a block allocation request used to come, it used to select a pipeline. And then for that pipeline, it used to query the number of the containers, open containers. And from these open containers, it used to select a container and then allocate the block. So this helped in providing a more balanced data write path. So even a random allocation of pipelines in the cluster would provide for much uniform block allocation. So then there are also some data improvements which have been done. So Ozone, as we know, involves GBs of data writes. So a typical data pipeline would have to perform data writes on GBs of data. Even the performance benchmarks require to write TBs of data. So we can't be wasteful with respect to memory in Java. Java GC can be can degrade the performance a lot in a typical Java process. So let's look at how some of these improvements in memory were made. So in a typical Raft configuration, as we discussed, there is a Ratus client which is communicating with the leader node. The leader node is accepting the client request and forwarding them to the followers. So if you see this configuration, the reader node is accepting the client request, and then it also has to pass these requests via network request to the followers. So it is for X amount of data being received from the clients. The leader is processing around 3x amounts of data. Also, leader has, or any data node leader would have a limit on the pending data writes. And this limit is usually around 1 GB. So any request which is exceeding this limit would be automatically failed by the leader data node. With the fixed retry policy, we were seeing a lot of GC pressure on the leader data node. So with the default configuration of around 3-second wait interval, the client on seeing a failure. So let's say the leader data node already has 1 GB pending data writes. On any further request would be failed now. So the client would keep retrying the request, and we could see a lot of GC pressure. And it was more of a bursty memory allocation and then garbage collection by data node. So in order to improve this, new retry policies were tried. In the new retry policies, we used more significant or aggressive backoff policies. So in case the leader data node was exhausting the available resources, the client would retry with exponential backoff. So the initial retry would be 4 seconds, then 8 seconds, 16 seconds, and so on. For other requests or other kind of failures, like not leader exception or some other Raft related failures, the client would retry with a linear increase in wait period. So for the first 5 requests, it would wait for 5 seconds. Then the next 5 requests, it would wait for 10 seconds, and so on. So this allows, with the linear backoff policy, it allows the leader to recover. In case the client is seeing a lot of failures to a particular pipeline, it will wait with increased backoff in order to allow the leader data node to recover. So with these policies, we saw a much stabler storage or data write pipeline in the cluster. Another improvement which was required was around buffer copies. So buffer copies, we use gRPC for data writes in the data pipeline, and gRPC uses protobuf. So we could see in the flame graphs that there is a buffer copy which used to happen in serialization and deserialization of these protobuf messages. This buffer copy has been fixed in the latest gRPC releases, and we still need to work on getting those improvements into Ozone. Then another problem which we discussed earlier was the leader is processing 3x amount of data. Combine that with serialization, deserialization, we can see that the leader would see 3x amount of buffer copies in the memory. So this buffer copy can take around 30% of the CPU time, which we saw in the flame graph. So in order to improve this, there is a project streaming pipeline which is going on. So the streaming topology allows for much lesser load on the leader data node. And in the new topology, it's a linear topology. So what that would allow is the first data node would receive the data request from the client. The first data node would forward that to the second data node, and so forth to the third data node from the second data node. So this is more of a linear transfer of data amongst the data nodes. So some other bugs related to memory. We saw that one of our cache implementations in Ratis was using a lot of retained memory. So what that means is the cache was used to store some metadata related to request. Apart from the metadata, it was also storing the actual data. So this data amounts in GBs of size. So what we saw in the data node was the data node would have a huge memory allocation, and then a GC would occur, and that memory allocation used to reduce. And then again, it used to see a huge memory allocation. So this was because the cache used to store these requests for 3 seconds. The expiry interval for any request was around 3 or 5 seconds. So the cache would maintain this request for 3 seconds, and while that request is kept in cache, the entire GBs of data is being stored in cache. So that improvement helped in reducing some of the retention of memory. Other issues are related to unintentional buffer copies. So it is possible that due to a bug, we were writing the data also to the log files or audit files. And then there are also other buffer copies which can happen in the cluster. So all those improvements were also made. So then there are also some one-line fixes. These usually require a lot of time, but the end result is that it requires only a single line of change in order to bring huge improvement in the system performance. So one of the earliest ones were around gRPC. So gRPC uses Netty for data transfer, and Netty assigns thread caches for non-Netty threads. So Netty has a library for buffer allocation. In case non-Netty thread is making a call to this buffer library, the Netty would allocate the buffer, but it will also assign a thread cache for this thread making that request. These thread caches have an on-heap thread pool as well as off-heap thread pool. So there is a Java property which Netty supports, and this property allows that the cache can be disallowed or can be disabled for non-Netty threads. So this Java property alone brought around 10x reduction in GC time from 3 minutes to 37 seconds. So this was very helpful in starting in the initial part of Ozone development. Without this, data writes would have been very costly with gRPC. Another one-line fix was around RocksDB. So what we saw with data node, so the data node was storing around 200,000 containers, and it was using a total memory of around 30 to 35 GB. So with JE malloc analysis and some other analysis, we found that the heap was only around 3 to 4 GB in the data node, and rest of the memory was being stored off heap. The JE malloc analysis showed that all of this off heap memory belonged to the RocksDB cache. So earlier we thought that this could be some RocksDB bug which we were encountering, but it turned out that it was a very simple naive bug in our system. So what we found that we were configuring the default cache size to around 64 MB. And by mistake, there was also another factor multiplication to this cache size, which was not very visible. So we were multiplying this cache size again by MB. So 64 MB into another MB. And we ended up configuring the cache size to around 64 TB. So this was like an unbounded cache. All of the RocksDB instances and all of the blocks in that RocksDB instance were being cached by the RocksDB. So once we made that improvement, the idle data node size reduced from 20 GB to 3 GB. So we saw earlier that on startup, the data node was consuming 20 GB of total memory. And now it was consuming 3 GB, which was totally on heap, and very little of that memory was off heap. With 200,000 containers, we were configuring, it's configurable to have how many containers we want in cache in data node. And we could see that if we could come to a classification on how many containers or how much memory is used with every 1,000 containers in the data node cache. So those were some of the performance improvements which we made in Ozone. In case of any queries or feedback, please reach out to me. My email address is ilchan@apache.org. Thank you.